In the 1960s, computing power was measured in tons. Machines like the ones in this photograph cost millions of dollars and took up entire rooms, serving as the massive processing engines for the military and elite universities. But despite their scale, these machines were isolated. Because there was no way to connect them, a computer in Massachusetts was effectively on another planet compared to one in California. If a researcher at UCLA wanted to run a simulation using a graphics computer in Utah, they had to copy their data onto physical magnetic tape reels, complete with a handwritten label, and put it in the mail. ARPA, the Department of Defense's research agency, wanted to fix this underutilization. J.C.R. Licklider, the first director of their computing office, envisioned a future of resource sharing, where researchers across the country could tap into any mainframe's power in real time. Realizing that vision meant turning the computer from a standalone calculator into a collaborative tool, a shift that required finding a way to link these incompatible islands of technology. The first obstacle was the heterogeneous host problem. Different universities used completely different hardware architectures. A 32-bit system simply couldn't communicate with a 24-bit system because they lacked a common digital language. The existing telephone network used circuit switching, which locks a single, dedicated path between 2 points for the entire duration of a connection. While this works for voice, computer data is bursty. It sends rapid pulses of information followed by silence, which would leave an expensive telephone circuit mostly empty and wasted. A researcher named Leonard Kleinrock proposed an alternative: packet switching. Instead of holding open a single pipe, data is chopped into small, independent packets. These packets are fired into the network, finding whatever path is available and reassembling at the destination. To manage this, ARPA developed the Interface Message Processor, or IMP. This gray mini-computer sat between the university's mainframe and the telephone line, acting as a buffer and a standardized translator for the network. These were promising theories, but they faced immense skepticism from the telecommunications establishment. To prove they worked, the researchers needed to move the concept out of the lab and onto a live wire. On the evening of October 29, 1969, 21-year-old student Charlie Klein sat at a terminal inside Belter Hall at UCLA. He was preparing to send the first data to a peer computer. 350 miles north, at the Stanford Research Institute in Menlo Park, programmer Bill Duvall sat at an architecturally incompatible SDS-940 mainframe, waiting for Klein's signal. The two men were connected by 2 lines, a standard telephone for voice coordination and a high-speed 50 kilobit per second leased data line that linked their IMPs. The goal was simple. Klein needed to remotely log into the Stanford computer by typing the word login. The data had to travel from Klein's terminal into the UCLA host, get packetized by the first IMP, travel 350 miles over the wire, get processed by the second IMP, and finally appear on the SRI host. Success would prove that incompatible mainframes could cooperate. Failure would confirm the telecommunications industry's belief that packet switching was a laboratory curiosity that couldn't scale. Klein typed the letter L. Over the voice line, he asked Duvall if it arrived. Duvall looked at his monitor and confirmed. He got the L. Klein typed the O. Duvall confirmed again. 2 letters were now sitting in the memory of a computer 350 miles away. But when Klein typed the letter G, the connection went dead. The SRI computer had crashed. At first glance, it looked like packet switching had failed at the moment of truth. But the diagnostic data told a different story. The network hardware, the IMPs and the data line, had delivered every packet exactly as intended. The network hadn't failed. It was the host machine. The SRI host was running an autocomplete program. When it saw the L and O, it tried to predict the rest of the word, login, by filling its memory buffer with the remaining letters. When the network delivered the actual G packet, it collided with the predicted text, caused a memory overflow, and halted the system. This crash was actually the proof the engineers needed. It demonstrated that the network was successfully decoupled from the computers it connected. The host had died, but the network layer had stayed alive. Duvall and Klein spent a few hours debugging the host software, isolating the buffer overflow and disabling the automatic completion feature. At 10:30 p.m. that night, they tried again. The word login passed through the chain without a single error. establishing the first remote session between two incompatible computer systems. For Leonard Kleinrock's Network Measurement Center at UCLA, this success provided the first real-world data confirming that dynamic resource allocation, sharing one line for many packets, actually worked. This experiment provided the evidence that packet switching was more efficient than the traditional phone company's circuit-switched model for moving digital data. It showed that computers didn't need a dedicated, permanent line to communicate. Because of that initial crash, the first word ever sent across the network was low. It was an accidental homophone for lo and behold, a fitting, if unintended, greeting for a new medium. By proving that incompatible machines could share resources through independent packets, this two-letter transmission established the basic rules for how computers interact today. The computing islands were finally and permanently connected.